All righty. This is what I start off with. And those of you who are filling out trivia sheets can quickly erase your answers and put in this one, because this indeed is the answer. Okay. So the, all right. Now I gotta make sure I don't trip myself. There we go. All righty. UNESCO designates each year as some special year, and in honor of the, I think, 150th anniversary of the creation of the periodic table, or at least the idea or something behind it by Mendeleev in Russia, is being commemorated. There's even a big conference in his memory in Russia next year, and so this is a very significant year, and it's very happy for me because the periodic table is what I sort of concentrate on in my work. Okay. If you wanted one slide to summarize what I'm curious about, it would be this one. And that is that we firmly believe that in the beginning, the universe, when it first erupted, created only the three lightest elements. Trivia question again, folks. All right. I'm answering half the quiz for you. Come on. But now we have this entire complex set of elements. And of course, we couldn't be here if it weren't for the rest of the synthesis of the elements, which goes along here. And basically, what I'm going to tell you tonight is just a breeze through of which kinds of stars, which physical processes create which elements in the periodic table. So you're about to see the periodic table an endless number of times in the next 15 minutes. Comment from me is almost superfluous at this point. But the other problem is, when I start thinking about stuff like this, I often, and I'm giving a talk, I often get so irritated that I forget what I was going to say. So I'm going to try to calm down for a minute and just put yourself back to your high school chemistry class. And the problem with chemistry classes is they have to make certain assumptions. And one of it is that the periodic table, the elements just exist. And that's the meaning of this phrase, this picture here. There's no questioning usually in high school chemistry of where the elements actually came from, because chemistry is basically molecular stuff, okay? And even when you get advanced chemistry things, like this beautiful book called The Elements, written by John Emsley. It's 500 pages, and they take a chapter for each element. In the introduction, they talk about the creation of the elements for 1/2 of one page out of 500, okay? And now I'm really irritated, okay. All right. But here's a different way to present the periodic table. It's always the same rows and columns, folks. To a chemist, you remember that the noble gases are on the right, hydrogen-like elements are on the left, and things are in between, okay? But here is the way a practicing astrophysicist views the periodic table. It's not which element has which valence electrons, but it's how those elements were created in the universe. And you see, they color code. For instance, exploding massive stars are responsible for things like germanium, arsenic, aluminum, you name it. Other dying low-mass stars. But you see that some of the elements have complex origins. And it's all a whole mixed master of certain things that create the elements, okay? And it's our job to try to disentangle this. We can do a really good job now, but it's taken 100 years to do it, okay? So, before I talk about which elements are made in which kinds of astrophysical situation, I think we need to pause here, because there's a person who gets very little credit in the general public, who actually was a gigantic scientist, but is largely forgotten today, and then Josef von Fraunhofer. Let's try that again. The important thing that people don't remember about him is he actually invented the spectroscope, the first working design of a spectroscope he was responsible for. And it shows him, you know, in an artist's conception, demonstrating the use of that. Now, most people, if they remember his name, remember that he's the one who trained a spectroscope on the sun, made a spectrum of the sun, and noticed that there were places that were missing, which we now know are absorption by elements in the atmosphere of the sun at different wavelengths and frequencies. Fine. Fraunhofer had no clue. This was before the rise of atomic physics. This was before a lot of experimental physics in the lab. Look, if he just invented the spectroscope, there's no way he could have access to other stuff that hadn't been invented yet in atomic physics. So he just labeled them A, B, C, D, and he basically someday we'll figure this out. Okay? By the way, he had the usual fate of an experimental lab physicist of his era. He inherited noxious gases in his lab. He breathed them in, and he died at a young age. Now, we all know about the story of the Curies getting radiation sickness, but it started way back when, before that, when things like mercury were routinely poisoning lab physicists. Okay, we've decoded them by now, but give credit to 100 years of coordinated effort by experimentalist theoreticians that I don't have time to go into. We now can identify what Fraunhofer called A, B, C, D, and I've just sort of listed a few. The so-called D that he saw were due to sodium, et cetera, et cetera. Again, that could be a whole talk by itself. So let's just go through. And the important thing is to take a look at the elements that are highlighted with yellow in each of these slides. As we talked about earlier, and as in one of the trivia question, the outcome of the Big Bang was simply a limited production of the three lightest elements. One of the reasons that it could only be a limited production is that the nuclear reactions that fused hydrogen to helium and helium to lithium were happening in an expanding, rapidly cooling universe. So the conditions necessary for fusion, which are millions of degrees, billions of degrees, very high densities, were just rapidly going away. So basically the production just stopped right there. So if that's it, we wouldn't exist. The sun, everybody talks about the fact that the sun is doing alchemy. Yeah, it is. But very few people talk about the fact that it doesn't do much. We know that the sun fuses hydrogen into helium and gains energy output to fight against gravity. We know that late in the sun's life, when it becomes a red giant, its core will then be taking that helium that it created and fusing it into carbon and a little bit of oxygen. That's it. Nothing more. Again, if only the production of elements from stars like the sun were going to happen in the universe, we wouldn't exist. Because you don't see any metals. You just see, again, it's concentrated down in the light end of the periodic table. Everybody who takes elementary astronomy, that they talk about the elements, learns really quickly that elements 3, 4, and 5 are really depressed in the atmosphere of the sun, other stars. It's not, those three elements are not made by stars. Matter of fact, they're easily destroyed by stars. That was a big headache for a while. Again, after 50, 60, 70 years, what they realized is that the lithium, beryllium, and boron that we get, and remember, lithium is an important element in things like medicine in the world. But that had to be made in the medium between stars where mature atoms, nuclei like carbon and oxygen, get pulverized by high energy cosmic rays. And that makes a little of it, doesn't make much else, but that's how we get those three light elements. So we build up all the way to element 8. Now what? Fortunately, some very low mass stars can essentially cheat their boring ends and die spectacularly. They must, however, have companions. So this is a cartoon of one of the possible ways that an eventual outcome that we know will happen to double stars, where they're both like the sun, and they both are either like white dwarfs or near to white dwarfs, they can merge. When they merge, they don't become boring, just hulks, remnants, doing nothing. And by the way, that'll happen to most of what the sun creates. It'll just sit in the white dwarf sun. It's gone. It didn't help a thing. But now, a whole range of elements that you recognize now, all the ordinary metals are made. It can be made, and they're made very efficiently in the blow-up of supernovae of a special type. And those special types, it took a while to figure this out, but those special types are involving the merging of two white dwarfs, or a white dwarf and another thing, a scenario that was considered incredibly unlikely to happen as recently as, say, 30 years ago. But it does happen. And that's where we get some of the ordinary metals. So if we had nothing but stars like the sun, and we at least allowed some of them to be close companions, close enough to actually merge at the end of their lives, then you might get some of the ordinary elements now that you need for life. Zinc. Ask me at intermission about zinc. It's the last of the ordinary elements. It's got an exotic use for human beings. And some of you may know what it is. Well, a lot of this is essentially ended now. What I really wanted to do was just emphasize that decoding from looking at a spectrum of stars, just what went on to create the elements, it involves a little detective work. It involves people like me just observing the spectra of stars and figuring out what elements are in the surface areas of them. It involves theoretical computations to understand that. I have a friend at University of Oklahoma that I've collaborated with for years who specializes in that. Atomic physics, nuclear physics, all sorts of stuff. But we believe that most of the rest of the periodic table is created in the deaths of very massive stars. And that basically they're the supernovae that you and I hear about on the news. They're ones, the massive stars, where there's a collapse of the core and a giant implosion followed by an explosion. As a matter of fact, it has a cute name. It's called the iron catastrophe. So more massive stars don't end their lives as white dwarfs. They keep building heavier and heavier and heavier ordinary elements in their nuclei. Nuclei of that is the inner regions, sorry. Nuclei and nuclei. Until they get to a magic element, iron. That should have been a trivia question. What would the trivia question be? No, okay, I'm limited in time. We could be here for a couple of hours till I got the right answer. Okay, look, the point is that of all the nuclei, iron, good old-fashioned iron, is the most tightly bound nucleus in the entire periodic table. So you can gain energy out by fusing light elements up to iron. You can gain energy by breaking up very heavy elements back to iron. But trying to do anything with iron as a nucleus itself, forget it. So when a star builds up to iron in its core, it's dead. The reason is, remember, the star could care less about alchemy. It was using the alchemy for the energy output to fight against gravity. When it gets iron in its core, the bottom drops out, because iron sucks energy in to fuse to anything heavier. It doesn't liberate energy. Implosion. The outer layers clamp down and explode outward. And in those explosions, the entire trace elements of the whole periodic table. So you got your trivia things out again? Okay. By the way, I asked the folks here, what if I disagree with one of the trivia answers? Does that mean you get it sort of taken off the quiz? Because the point is that we think that what is happening is the creation of the things like lead, platinum, silver, gold, lanthanum, and there were headlines about this a few months ago. We think that the merging of two exotic neutron stars results in the outer layers sort of exploding out into the universe and making the exotic heavy elements. Notice the protective legalistic clause in the way I see this. We think. And the point is, stay tuned, folks. And that's the happy thought here. I think I can name most of the elements in the periodic table. I think I know the origin of a lot of them, but we still got tons left to do. And what I like to think of is the three last slides I like to think of. One is that every time I see this, yeah, I see this beautiful image. But what I'm thinking also is, oh, look at all the elements that I can think of that have exploded away from that ancient event that happened. And I'm seeing what's happening is I'm not seeing the death of a star, I'm seeing the creation of elements for new life. I also am fascinated by the kind of stuff I do because it involves scales which are the smallest to the biggest in the whole universe. It goes down to atomic nuclei, the smallest, one of the smallest things you can imagine. It goes out to the whole galaxy. So all that is just, I never could conceive of that when I was growing up, that I'd have so much fun with his length of stuff, this imagined scales of size, mass, anything like that. And finally, I'm sorry, the people who should have been here tonight talking to you are Carl Sagan and Neil Tyson. Instead, you got me. So we all know what Carl Sagan said about the elements, right? We are all stardust, right? No, I wasn't going to do that tonight. Here's what I'd rather leave you with. I think it's a more elegant statement and a more thoughtful statement. And the joy here is that this happened and that we can be involved in actually trying to decode it. And it was fascinating when I was a UT grad student in the early 70s. It is fascinating now that I'm in my 70s. It's a really neat thing to do. And I hope to be still confused 20, 30 years from now. Okay, thank you.
All right, let's take some questions for Professor Stardust. Who's first? Okay, up at the top.
I'm sorry.
Could you say that one more time, a little bit louder, sir? If Jupiter and the Sun merged, are they large enough to do something interesting in terms of talk? Repeat the question, please.
If Jupiter and the Sun merged, you've got the wrong speaker, okay? But here's what I think I can say that actually makes a little bit of common sense, because I've actually never considered that question before. So I'm going to assume you mean our sun, and then something happens, that something flies by Jupiter, and suddenly it gets a nudge to come into the inner part of the solar system, and it gets swallowed by the sun. That is an active research area, folks, in the following sense. And how many hours do I have left?
A couple.
Sorry, yes. Okay, to continue, he said, look, lithium. Most stars destroy lithium. So the idea would be if a planet which is full of undestroyed lithium from the creation of that solar system gets swallowed by a star, its parent star, then for a while that lithium will stay on the surface before it gets convected down and would be destroyed. So one of the idea is to try to look to see which stars have excess lithium and see if they have planets around them. Now, the planets, as someone said to me, if they have planets around them and they have a lot of lithium, that's a good place to search for extraterrestrial life, right? Because some of the inner planets have been swallowed and people on the outer planets are screaming for help, right? But the point is, your question is very apt, and it centers on one element exactly, and that is lithium.
All right, great question. We got time for one more? All right, up front.
All right. Your periodic table of the elements, you showed a map of all of the elements with certain elements grayed out, which I'm assuming that are pigment elements. One of those elements was titanium, but I do remember reading a few months ago that there is a, I do remember reading a few months ago that there's a source for titanium in stars.
Yeah, another excellent question.
Please repeat it.
How much? The question is about the element technetium. And he had read something about that being very important to actually sort of proving that stars do make the elements. And it is. In 1951, 2 sentences of a paper devoted to anything else except technetium simply mentioned, oh yeah, in these red giant stars we found some of them have technetium. And then went on to other subjects. And that changed everything. I believe the paper was 1952 or 53. The author could have cared less. But what it means is the following. Technetium is unstable, just like you noted. It doesn't last very long. But it lasts long enough to be interesting. I think it's something like 100,000 years or something like that. So our sun's 4.5 billion years. Any technetium in it? Nope. Any technetium that it was born with, long gone. We see some red giants with technetium up in their atmospheres. That technetium had to be made inside that star. Otherwise, it would be gone. With one fell swoop, that paper that was interested in anything else proved that stars are actively, at this point, making the elements.
All right, great questions. If you have any more, you can find Professor Stardust over at the table during intermission. Thank you, Chris.